Good evening, everybody. My name's Andy Stevenson. I'm the chair of the Teesside Committee of the IMechE, and I'm pleased to welcome you to what is our 10th technical talk tonight. So the subject tonight is on the Boston Barrier, and the presentation is going to be facilitated by Paul Griffiths, the founder of Teesside-based Industrial Marine Hydraulics. We've got a number of other speakers tonight, and Paul will introduce them during the course of the presentation. Our next event is the third in a series of professional development talks on the 10th of November, and you can sign up to this via the IMechE Near You website. As always, if you would be interested in giving a technical talk on any mechanical engineering subject, we'd be delighted to hear from you. And you can get in touch with myself via the email address below or via the IMechE Near You website. I'm going to hand over to Paul shortly. If anyone's got any questions during the presentation, then please submit them via the question box, and we'll go through them via a Q&A session at the end of the talk. So I'll now hand over to Paul Griffiths of IMH. Over to you, Paul.
Thank you, Andy. Members of the IMechE, ladies and gentlemen, my name is Paul Griffiths of IMH, and a warm welcome to our presentation. Accompanying me is our engineering manager, Ian Bannister, and we are very pleased to have been invited to present. We're also very fortunate to have with us Adam Robinson, who is the Boston Barrier Project Director for the Environment Agency. We're going to talk about the challenge and problem. The EA are dealing with a number of areas in the UK where flooding is a severe problem. Boston is one of those locations. The engineering solution presented to us. There were many creative ideas proposed by some experienced professionals, and we are going to talk about the solution that was applied. Why IMH? Well, IMH was selected as the hydraulics partner because we have decades of experience in this sector and with this type of challenge. Our engineering challenges, well, there were many, and we are going to talk about lifting one of the largest barriers in the UK into position in a very short time frame. Our project approach, we will explain our approach to project management, some of the key technical decisions we had to make, and how we ensured successful installation and commissioning. For those who do not know of IMH, we're a global player in hydraulic engineering. We help customers overcome challenges and successfully meet their objectives. We deliver major hydraulic engineering projects and offer services across the whole spectrum of hydraulic engineering. We design, we manufacture, install, commission, maintain and repair, component supplies including distribution, training, very much internally and then externally. And I will now hand you over to Adam Robinson of the Environment Agency to begin.
Thanks very much, Paul, and for the great introduction. As is always the case with these things when we go virtual, my webcast studio has just died. So I am going to talk through, but we might not be clicking through on the presentations as we go, but I'm currently reloading as we go. So yeah, thanks very much for that introduction, Paul, and thank you for inviting me along today. I'm Adam Robinson. I'm the Project Director for the Environment Agency on the Boston Barrier scheme. What I've been asked to talk through is what we're doing. So the challenge that we've got in Boston is we've got a long history of tidal flooding, where the town flooded from 1953, 1978, and most recently in December 2013. And the town actually relies really heavily on existing tidal flood defences. The Boston Barrier, which we're talking about, has been in concept as far back as 2005, but became much more prominent following the surge in 2013, when we became a UK infrastructure priority project, which was broadcast in the 2014 government autumn statement, where we were given guaranteed funding to deliver the project that we're on today. The photos, which I hope you can see on the screen, because I can't, shows the floodwater in the town centre in Wormgate at the top. That was on the evening of the 5th of December 2013, and the aftermath of what the flooding causes. So this is one of the residential streets called Pulvertoft Lane in Boston. And that image just shows the devastation that a flood can cause, and that's just 3 weeks before Christmas that residents have to deal with. At the moment, flood defences through the town centre average around 6 metres AOD. The new Boston Barrier and associated works, which we're currently installing, run in at 7.55 metres AOD, which is the forecast flood defence level that we will require in Boston for the next 100 years, or taking us out to 2120, and this takes into account climate change allowance. The 2013 tidal surge reached 6.08 metres, so the devastation that you can see in those photos occurred through an overtopping of defences of 80 mil. That damage was incurred over about 800 properties across 55 streets in Boston town centre. If the Boston Barrier had been in place on the 5th of December, it would have prevented the town from flooding that night. So this obviously galvanised the need for the barrier. The next slide that we've got just demonstrates how much of an impact on the local area we have. So we issued 18,500 flood warnings to local residents and businesses on that evening. As I've said before, the scheme will offer an enhanced level of protection, and we're talking a level of protection equivalent to or as high as London, so a 1 in 300 year level of protection, hence the need for that 100-year design life of the scheme. So through the delivery, we will better protect over 14,000 properties against tidal flooding, and that includes over 700 commercial properties. Delivery will generate economic benefits to the local community in the surrounding area in excess of £1 billion. So through what we see as quite a reasonable investment now of £100 million, we deliver in excess of that £1 billion investment to the local economy and area. Boston is at risk of both tidal and fluvial flooding, which means there's a real delicate balance to take into consideration when thinking about any new defence. And as you can see, with the workable Boston Barrier in place, it will have one of the best standards of protection outside of London. Hopefully you can see the next slide, which shows a number of different locations from A to E. So we considered a huge swathe of options on where we were going to deliver the barrier. We've got 2 main watercourses, which you can see in the top right-hand corner of the screen, which is the River Witham, or the Lower Witham, which runs from Grantham to Lincoln and discharges out via the Grand Sluice in Boston into the tidal haven. We've also got another main drain, which helps drain the local agricultural land called the South 40-foot Drain. But in addition to this just being a Boston Barrier tidal flood defence, it also has longer-term ambitions to link in with strategic water level management in the area. So what we'd like to do, and what we're continuing to do, is work with navigational authorities to deliver a non-tidal link between the Lower Witham and the South 40-foot. And that strategic ambition is therefore to link Lincoln, Peterborough and Ely as cathedral cities. So that not only will that help deliver a navigational watercourse, but it will also help encourage growth and income and recreational use in those cities. So originally we looked at location A. Unfortunately, that was discounted early on, even though there's huge amounts of benefits for it being a smaller structure, being a little bit easier to construct. It didn't meet that long-term strategic ambition of generating that non-tidal link between the Lower Witham and the South 40-foot. Point B is actually where we're building our barrier at the moment, so I'll cover that off in a moment. Option C is the location further downstream, which impacts, as you can see in this picture, there's the Port of Boston. So the Port of Boston, as one of our major stakeholders, was really keen for us not to impact on their outer berths as much as possible. So obviously any further movement of the barrier downstream removed a number of their external berths, which would potentially prohibit their future use. Option D, and we've got a third watercourse here discharging by the Maud Foster Drain, and as you'll notice is also downstream of the wet dock entrance. So again, at option D, we not only then have to contend with the Maud Foster outlet, which is a grade 2 listed structure, we also then have the need to manage through construction the impacts of much larger ships entering the wet dock entrance at the port. So the structure itself becomes substantially larger, the protection required to against the vessels up to 100 metres long and 16,000 tonnes. So the engineering and the cost of the project goes up. We then had option E, which is basically from the bottom of the screen all the way out to the mouth of the wash. Now there's a lot of people, including the Port of Boston, the local fishing fleet, and other residents that were really keen to have it further out of town because they see it as enhancing the level of protection to Boston. Unfortunately, this wasn't the case. Not only do costs go up, but the infrastructure further out to the wash in the agricultural land just isn't there. The highway infrastructure would all need upgrading to bring our materials and our construction equipment in. The power supplies to run our project aren't there, so again, we need to bring those in. So the cost of delivering that just goes up exponentially. In addition to that, we've obviously got the wash, which is a triple SI, a SAC, an SPA, a Ramsar site. So getting approval that far out is really difficult, as I'm sure you're all aware. And the ground conditions from a geotechnical point of view are not that great further out to the wash as well. So on to the next slide, we start covering off some of the benefits of what we're doing. So we've split the project down into 4 sections. So part 2 is the right bank, which is the blue line you can see here, where we've installed 14 kilometres of piles if you line them up end to end. It's about 1,200 metres or 1.5 kilometres worth of steel on that right bank. And what we've done is we've taken our existing standard river tidal bank and we've reinforced it with steel sheet piles, which has brought us up to that 7.55 metres that we need. Then we get on to the kind of the piece to the resistance, the primary flood defence barrier that you can see in the middle of the picture there, which was designed as a rising sector gate. So it's 25 metres clear opening, 300 tonnes, and is operated off 2 hydraulic rams, which I know Paul and Ian are going to cover off later in today's presentation. We then move on to the left and right bank. So we've got the left bank running down the tidal haven, and this is more of a standard construction methodology where we've got reinforced concrete flood walls, floodgates, and we connect into what is going to be a new wet dock entrance gate for the Port of Boston. So that new gate there is going to be slightly wider than the existing one, but involves the works that we're moving on to now in the new year, which will involve a temporary dolphin, a turning circle. So all those vessels that we've talked about earlier, up to 100 metres long, will be turning off this dolphin, and they'll be mooring on the new left bank keyworks. So, on to the engineering solutions. As we've said, it's a huge civils project for Boston and the surrounding area, in excess of £100 million. The barrier gate is 25 metres wide, just over 300 tonnes rising sill barrier, which is raised into position by those 2 hydraulic rams. Those rams are 55 tonnes each, contain 300 litres of biodegradable oil, and our 16,000 litre hydraulic system, which we use a paneling oil within. That primary barrier is there solely to protect Boston and the surrounding area. And we needed to construct the cofferdam that you can see on the left-hand side of our slide to actually dewater the area, excavate it out to a suitable level to allow us the superstructure that it sits within to be constructed. So the next slide that we move on to is, sorry, at my end, is some of the engineering solutions that we've presented. So we've had a number of key learning points on this. So we've got a sister barrier to Boston down in Ipswich, slightly smaller, about 20% smaller, but we took a lot of lessons from our supply chain on some of the problems that they encountered on there. So one of the key ones was the tight tolerance on the curved invert that you can see in the picture on the left-hand side. That curved invert took a huge amount of temporary works down in Ipswich and a lot of headaches in pumping, as I'm sure people are aware, pumping concrete onto an inverted curve. So working through our supply chain, we looked at precast units. These were not only much easier to fit, but they actually came in one lump. So they were precast over in Ireland through our supply chain at IMechE, brought over by a lorry, and they were actually installed in 3 days. So we managed to construct the entire invert of where the primary barrier now rests within the cofferdam in a 3-day period. In contrast to Ipswich, it took in excess of 3 months to construct that same invert. So using that methodology of learning from our peers and from our colleagues, we've come up with a really good innovative solution for that. In addition to that, the whole project has got a full BIM model associated with it. So we've got the usual clash detection for a more efficient and effective way of constructing things. So that clash detection is detected early before we actually get out on site. We also prefabricated a lot of our reinforcement off-site and brought it to site and lifted it into place, not only for the benefits of speed on the programme, but also from a health and safety perspective. As I'm sure you can see on these pictures, it's a really highly reinforced structure and very congested. We were concerned about health and safety for our steel fixers within the structure, that should there be an incident, and how you get them out quickly. So what we tried to do, and what we successfully achieved, was limiting their time spent within cages by prefabricating it. So we quite like that when we coined the terminology, build it twice. We built it once on CAD, and we've tried to break it so many times it's ridiculous. So that when we built it for the first time in real life, then we hopefully had come across and solved as many of the problems that we could foresee as we could. But for the interesting bit now on the mechanical and electrical elements, I'd like to hand you back over to Paul and Ian to go through the challenges and solutions which IMH have worked through to deliver this outstanding project and the primary defence barrier for us in Boston. Thank you very much.
Thank you, Adam. Ian Bannister and I will now take you through our part in this prestigious and challenging project. So why involve IMH? Well, with 35 years of experience engineering the hydraulics on several flood defence and gate systems, including Black Sluice Lock, Boston, pictured right, and just up the river from this installation, Heybridge in Essex, Palmer's Dam in Devon, Canvey Island, Holehaven Barriers in Essex, there are 3 of these, Ipswich Lock, including a central floodgate and swing bridge system, also pictured, Tilbury Flood Defence Barrier in Essex as well. And all of these were with the Environment Agency. We've been involved in many other high specification projects which assisted IMH to win the barrier contract, including wind farm jack-up vessels and large deck spreads, the pioneering Spirit, a very large heavy lift vessel, a deep well capping system following the Deepwater Horizon oil spill in the Gulf of Mexico, several subsea engineering, pipe and cable, lay and recovery reel drives, power stations including nuclear, upgrades and ongoing support for EDF and others. And now to the barrier and Ian Bannister.
Good evening, I am Ian Bannister, the Engineer Manager for Industrial and Marine Hydraulics. I was the Project Manager for the hydraulic system. The simple sketch shows the barrier closed, also known as the flood defence position. The barrier is fabricated with over 330 tonnes of carbon steel. When the barrier is at full ballast, it weighs approximately 703 tonne. The ballast utilised is water. It is over 10 metres high and 30 metres long, with a specified operating time of 20 minutes between the open and closed positions. This needs to operate with a fluid temperature range of between -20 degrees and 50 degrees Celsius. The hydraulic system is a hydraulic closed-loop solution. Paul will discuss this in a little more detail later. The modes of operation are in the open position at the bottom of the riverbed, closed, deployed into the flood defence position, the flushing position, allowing cleaning of the base, inspection position at low water, and maintenance position. It's probably the most challenging of all. And finally, a water management position, which may be a requirement. Thus, the barrier is also future-proofed. So, let's consider the size of this structure. The next slide has been used for a wide range of audiences to give some size to the sheer scale of the barrier. As indicated in the slide, the barrier is approximately 6 double-deckers in size and the weight of 93 very heavy elephants, or 706 tonne, when full of water during normal operations. As you can imagine, this is a very large moving barrier supported by an equally large civils infrastructure from the joint venture partners BAM Nuttall and Mott MacDonald. And now to the hydraulics. There are 3 very large cylinders in total, including a spare cylinder that is installed in a separate GRP enclosure and can be operated from the main hydraulic power unit. The spare cylinder is designed to have the ability to be installed on either side of the barrier. It achieves this by having a bracket on both sides of the cylinder. The cylinders are 860mm bore with a 400mm rod and over 8 metres of potential stroke, weighing approximately 57 tonnes each. The main system cylinders are installed with full stroke LVDTs, linear variable differential transformers. These are used to provide cylinder positional feedback to the PLC control system. The cylinders are supplied with hydraulic control manifold blocks, which were designed and supplied by IMH for incorporation into the cylinders prior to delivery. They are believed to be the largest manufactured in Europe. The main load is to the annulus, requiring a maximum pull force of 9,487 kilonewtons. That's not much less than 1,000 tonne of pull force each. This highlights the benefit of utilising hydraulic systems as a power source. The power to weight ratio advantage of hydraulics. Each cylinder weighs in at around 57 tonne with a pull force capacity of 1,000 tonnes.
So from concept to build, the hydraulic solution for gate movement was developed initially by Mott MacDonald and Ban Nuttall. From an exemplar circuit, IMH created a final detailed design and circuit diagram. We then designed and built hydraulic power units, or HPUs, and control manifolds to power the barrier. We sized and selected all components to suit the specified temperatures, calculated pressures, forces, and speeds of operation. All was 3D modelled into arrangement and detailed drawings. As Adam has said, the fluid is environmentally friendly or biodegradable, and that chosen is Panelin HLP Synth 22, a synthetic hydraulic fluid. It's expensive, but does what it says on the tin, and leaves no harm to the environment in the very unlikely event of a fluid spill. IMH designed and built 3 hydraulic power units to power the barrier. The main unit is shown here after testing at IMH Works and before dispatch. This is 172 kilowatt with proportionally controlled axial piston pumps, boost pumps, and a full suite of instrumentation, filtration, etc. There were also 2 emergency hydraulic power units, each driven by a 45 kilowatt diesel engine. The cylinders are approximately 30 metres apart, and parallel movement of the barrier is important. Under normal operations, each cylinder position is controlled using the cylinder linear voltage differential transformers, or LVDTs, and electronic proportional control of the axial piston pumps. This hydraulic circuit includes load control valves, but was also specified as closed-loop hydraulic control. And due to the large cylinders and fluid volumes, this significantly reduces the tank sizes, important in the unlikely event of fluid loss to the environment. The emergency features, or redundancy, are built into the design, and we have included 2 cylinders plus a spare. But this barrier can be operated on 1 cylinder only. 1 main hydraulic power unit, but multiple pumps allowing for pump loss. 2 diesel-driven emergency hydraulic power units, manually controlled, but only 1 is required to operate. The 2 necessary pipes crossing the river to the right bank are doubled to 4, therefore 100% redundancy. Ian will describe this in more detail. A manually controlled gravity fall from deployed to rest. The render of the HPU is shown, and it is elevated because it is on the first floor of the control building. This to ensure it will always be above the floodplain. Nothing has been left to chance, and the message from all parties, the Environment Agency, Ban Nuttall and Mott MacDonald, has consistently been Getting it right overrides all. When this barrier is needed to operate in anger, it will.
Stainless steel welded pipework totalling over 800 metres. Due to the complexity of the civils work, the requirement for an extensive amount of reinforcement and issues with the weather, the civils programme was under pressure. Coupled with this was the uncertainty with procurement due to Brexit. IMH proposed forward purchase of the associated materials and a fully prefabricated solution. Utilising the Revit models supplied by the joint venture, IMH utilised 3D design to create fabrication drawings and procured the material early. The complete fabrication of the 800 metres of stainless steel pipework was in a dedicated stainless steel facility on Teesside. This was to prevent cross-contamination. As a result, the programme was recovered with time in hand and the pipework installed on site within the civils, with a minimum of site joints all pre-flushed and proof tested at works before dispatch, showing the benefit of the hard work by BAM Nuttall to produce an accurate civil structure to the tolerances promised. This was so successful that even with an excess of 800 metres, only one pipe required modification on site. The pipework installed was also larger than usual because of the -20°C specification and associated higher fluid viscosity. This was to reduce the pressure drop of the system to approximately 5 bar at the increased fluid viscosity of 680 centistokes. As Paul touched on earlier, the normal viscosity is around 22 CST at 40 degrees Celsius. The river was reduced to half width using the cofferdam mentioned by Adam earlier. This then required a significant temporary pipe bridge to be installed over the rerouted river to allow the system to be commissioned and proven prior to diverting water through the barrier. The main hydraulic power unit is on the left bank only, within the control building, and a pipe crossing was required to the right bank cylinder. Pipework such as this, fabricated and installed inside civil structures, has been known to be troublesome because of almost zero access for repairs. This may also be installed through a culvert or tunnel from side to side, again with inherent problems and expense. To overcome this, the decision was to utilise a novel approach to connect the left bank and right bank. This became known as the Big U. The Big U was a name given to our joint solution as seen. This is a prefabricated structure incorporating a pipework of 2 service pipes and 2 additional spares running in parallel. The whole structure was fabricated from 3D modelling and relied on the civil's dimensional accuracy, which was excellent due to the skills of those involved. A special lifting beam was fabricated. This enabled lifting and lowering of the assembly into position. The design of the mechanical structure and associated hydraulic systems enables a full replacement in one piece, should this ever be required. The model shows an overview of the pipework, both emergency hydraulic power units, the pipework within the temporary pipe bridge, and the Big U. The photo shows a cast channel in one side and the base. The Big U was installed into the basin, fully tested and flushed in one piece, then further pressure tested in position to prove there was no mechanical damage during the installation process. Another view also showing the left bank emergency HPU. Big U cast channel and pipework from the control building. The emergency HPUs are shown without their installed GRP enclosures. This is to give visibility of the unit. The emergency hydraulic power unit is installed with a 45 kilowatt diesel engine. There is one manual directional control valve on the unit which can operate the barrier. The cylinder installed on the opposite side is put into float mode. This allows the cylinder to follow.
So now let's have a look at the barrier operation. First, using a model. We now know that the modes of operation are at rest, deployed, flushing, inspection and maintenance, with a future potential for water level management should it be required. Here it is at rest. Green, of course, is the barrier. So let's see it move. And from the rest position, it's going to pass through the deployed position and go immediately into the inspection position. Here, the safety latches will be engaged, the pins will be removed, and the link arms lifted clear. The cylinders will then be extended again and reattached to the barrier, as can be seen there. And the final movement is to raise the barrier directly into the overhead and the maintenance position, which of course is 180 degrees from the start position. Now this is only a model, but please remember the double-decker buses, the elephants, and only two 57-ton cylinders. This is a significant barrier. For now, the plan is for the barrier to only be raised at peak high tide, which is around 1 to 3 times a year. It would also be raised, of course, for inspection and maintenance purposes. The frequency at which the barrier will be used will increase as time goes on, and for example, the Thames Barrier in London is now used hundreds of times a year. And now the real thing, with a time-lapse video. First though, even though this is a fisheye type lens, you can see the dark recesses vertically either side in the civil structure in the foreground, which is the big U in position, and the base or sill crossing can be clearly seen to be covered. And now the movement. Just leaving the rest position. Notice the size of people to help gauge the barrier size. Normally taking 20 minutes in real time, and it's seen here approaching the flood position, the flood defence position. But imagine this raising a further 90 degrees into the maintenance position. When fully deployed, a very important flood defence for Boston and the surrounding areas. Impressive, I hope you agree, and we believe the largest in the UK. Installation was a challenge, and these photos give an insight into initial mechanical installation. The site and cofferdam area didn't have room for a crane that could lift a structure of this size. The solution? Don't use one. SPMTs, or self-propelled modular transporters, were used. These were loaded and secured onto the barge together with the barrier in Holland, and on arrival at the highest tide level, the barrier was slowly and carefully driven onto the cofferdam and positioned in place. The barrier had to arrive on the highest spring tide. If this was missed, there would have been a delay of possibly 4 months to the project. Commissioning was also a challenge. It's always an interesting time for a project, but the real challenge here was that the barrier was delivered by barge, but in the fully raised maintenance position, the most challenging position that the barrier is ever elevated into, as demonstrated with the model. Commissioning is normally gently does it, and in a lifting solution this would be raise a little, then lower back down, a little more and back, etc., etc., until full confidence and control is achieved before the first full raise. The real concern here was that the first movement was the worst possible position to take it from, the fully elevated, and then lower it to the inspection deployed. All was done, of course, very, very carefully after thorough bleeding of air from the hydraulic system, proving the control system before the barrier was connected to the cylinders, and of course very thorough testing of the hydraulic controls over several weeks. During commissioning, it was proven that the accuracy of cylinder stroke was parallel to within 0.1 millimetres of each other, even though 30 metres apart. Clearly, only achievable with electronic closed-loop proportional control. And to our last slide as we approach our presentation close. 1. The scenario of repeated immense flood damage to Boston and surrounding areas. 2. The need for a significant flood defence barrier. 3. The challenge to raise this monster using hydraulic cylinders in 20 minutes. And 4. The solution with 3 HPUs, electronically controlled, significant safety backups, 800 metres of stainless steel pipework, and using the Big U approach for future major maintenance protection. And now I'll hand you back to Adam, who is going to close for us.
Thanks very much, Paul and Ian. Really interesting insight into the works that IMH have done. Just before we close though, we'd just like to run over a final bit around the UN Sustainable Development Goals. For those of you, I'm sure you're all cited on them. I certainly wasn't, however, a number of years ago. 2 or 3 years ago now, I was asked to present to our Environment Agency board on UN SDGs. And we were asked to do a retrospective look at the Boston Barrier on how we met the development goals that you can see in front of you. So at first glance, when I undertook this piece of work, I looked at those 17 objectives and went, how on earth does a coastal flood defence barrier meet objectives like no poverty, quality education? The easy ones you could tick off were life below water, climate action, life on land. But some of them are really difficult to look at. However, on face value, there's the 17 objectives. Underneath that, there's another 169 targets. And the reason why I want to briefly touch on these today is because this is something that we're looking at corporately, and it's becoming more of a objective. So we are looking to release some primary and secondary objectives, which we would use to work with our supply chain with and our partners in the future. So within those 17 primary titles, as I said, there's 169 subheadings. But when we started looking at them, we found that we could easily provide evidence under all 17 of those objectives. So, for example, what we did was on the 3 that we like to pick out in no particular order are industry, innovation and infrastructure, partnerships for goals, and quality education. So we do a huge amount of work with the local community, the local schools. So we've got registered STEM ambassadors, and the supply chain and ourselves go out to local primary and secondary schools to promote not only the work that we're doing from an engineering perspective, but also around how we better protect businesses, and which leads to enhanced employment and economic prospects. Partnerships, we've had a Boston Community Hub on site since August 2015. It's where we have every Wednesday, pre-COVID this was, where we'd open it to the public between 12 o'clock and 7 o'clock in the evening. And this is to ensure that we're engaged with that local community, we understand what they're talking to us about, and we can appreciate their position, and hopefully if we can change things on site, then we will. In addition to that, since the commencement of works on site, we've invested in excess of £6 million to date within a 50-mile radius of the site, and that is in the local supply chain, so for everything from hotels to concrete suppliers to the port, to aggregate suppliers, etc., etc. So we're really pleased around that betterment that the local economy has got from our work in the area. And then also fundamentally, the scheme objective is to reduce the flood risk to local assets and businesses. It's a key objective for us. So obviously the industry, innovation and infrastructure is where we are. So finally, just to close, I'd like to take the opportunity to thank the Institution of Mechanical Engineers for facilitating this afternoon's webinar, for IMH for their work on the Boston Barrier project to date in providing their expertise to enable the operation of our new asset, and for Andy, Paul and Ian for inviting me to present with them today. This scheme is the culmination of many years of hard work and expertise. We can and will continue to deliver great outcomes for people and the environment by working together in collaboration, so that we will better protect and prepare homes and businesses from flooding and coastal change, whilst also creating climate resilient places. Thanks again for listening, and do follow all of our social media feeds for continued updates on the project, and we look forward to answering your questions. and it hands you back to Andy for the Q&A session.
Excellent. Thank you very much, Adam. Thank you, Paul and Ian as well. We've got a few questions have come in already. If anybody else would like to ask a question, please feel free to submit it. First question, I think, is probably to Adam. Someone's asking, is the barrier operational yet? And if it's not, how long will it be before it's up and running?
Yeah, Andy. So yes, the barrier is operational. We have just this week, I believe, come online now with our primary power supply. So we had 2 spring tides in September and October where we could deploy the barrier against a tidal flood surge if it occurred on emergency HPUs. But we're now on mains power, so yes, we are operational from now.
Excellent. Okay, and then a couple for either Paul or Ian on the technical side. You showed a picture of the large cylinders. What sort of coating was used in the piston rods?
The coating used on the piston rods was it's very commonly used in this type of environment. Ceramic coating. The manufacturer of this cylinder has a trade name for it, calls it Ceraplate. But as I say, it's very common in this type of environmental condition for protection against seawater, brine, and also fresh water. So the rod coating is ceramic. Thank you.
Okay, thank you. And then a second technical one, probably for you again, Paul. Was there a noise specification that had to be met for the project? And if so, how did you go about achieving that?
Yes, there was indeed, as in most, in fact, I think all hydraulic systems, all systems, in fact. The spec was 85 decibels maximum. I don't have the actual figure to hand of what we achieved, but I can actually tell you that we murdered it. We achieved it by using basic but good hydraulic power unit build design and care, but also the piston pumps, proportionally controlled, are also well known to be relatively quiet. We used low speed 6-pole motors, which run, as we all know, at nominally 960 revs per minute, whereas often 4-pole are used at 1450. That reduces the noise significantly. Internal gear pumps for boost, pilot and filtration. These were internal gear pumps, as I've just said, but they were also further enhanced because we chose helical internal gear pumps, and those as well were very quiet. So very happy with the noise levels. Thank you.
Okay, thanks, Paul. I think this one's probably one for Adam. Somebody's asked if there's been a reassessment of the flooding scenario used as a design input based on our latest understanding of climate change.
Not on the latest one. So our UKCP 17 data, I think we've reassessed against, because we're already under construction. It was deemed. We will obviously relook at the latest data. However, when we looked at the last lot just before we began construction, we were still within the climate change forecast scenarios. So there was no reduction in that level of protection that we were providing through the construction of the Boston Barrier Works. So we haven't done a full reassessment, but we've done a check against the last data. Okay, and kind of as a bit of a follow-on question to that, Adam, are there any other areas of the UK that are currently being looked into for a similar type of barrier design? Yeah, barriers seem quite popular at the moment. So we've got another set of barriers over at Bridgewater on the west coast, just down from Worcester on the Severn. They are currently going through a Transport Works Act order application. And then we're also working on some options down for the low barrier down in Cornwall as well at the minute. Okay. So someone put a comment about the Thames Barrier, which appears larger than the Boston one, and the question is just how does that compare, and was any learning taken from that project in the past? Yeah, so Thames Barrier is their primary gates are much larger than what we've got at Boston. We did a lot of our learning from Ipswich Barrier, which I mentioned earlier because it was very similar. in its operational remits. We do work really closely with Andy Batchelor and his team on the Thames Barrier. We are looking at efficiencies in inspections, so confined space inspections and new and innovative ways of doing that. And then we also link in with the Thames Barrier on an international basis through a network called iStorm, where we do learning with the likes of the US Army Corps, like Waterstaat in Holland, and the Moses Barrier over in Italy as well, with a team over there. So, and then we've also been inputting into a new tidal barrier over in Singapore. So we do a lot of lessons learned across the entire network, not just in the UK, but internationally as well.
Okay, I'm not sure who's best to answer this one, but you've mentioned the Ipswich Barrier a couple of times. So somebody's asked, is there a reason why a horizontal arrangement was used for the cylinders that differs from the Ipswich Barrier? And does the horizontal arrangement lead to any concerns on the cylinder seals?
I suppose that's one for me again. The reason we went for horizontal hydraulic cylinders was because we were uncomfortable with having the barriers submerged in the saline water environment. So we saw that as a potential risk in the long term for the seals and for corrosion potentially. So we looked at moving, or we have moved them to a horizontal arrangement. In regard to the durability of the seals, the information we've got is that the seals, the way they're set up on the gimbal, etc., there's not a huge amount of pressure on those seals that would cause us concern for leakage. I don't know if that's one that maybe Paul and Ian can comment on in a bit more detail.
Yeah, we're happy to enlarge on that. Modern low friction seals are much happier than in the old days when we had very heavy chevron packings, and cylinder manufacturers these days are much happier with horizontal installations. There are obvious advantages of vertical, but then you've got to balance that against the disadvantages, which Adam's just spoken. Major one, of course, is keeping the rods out of the water. So you balance one against the other, and we think that the horizontal one is clearly the beneficial one. But modern seals, cylinder manufacturers don't seem to have much. They don't seem to object to it these days as much as they may have done the other day, years ago. But yeah, not a problem at all. We accept that this is a good solution for this barrier. Thank you.
Okay, thank you. This might be one for you, Adam, in terms of some of the background to the design. Someone's asking if a counterweight system was ever considered, or a hydraulic accumulator, with respect to the sizing of cylinders.
Not that I recall. We didn't look at counterweight. So I think because we had Ipswich operating with the vertical hydraulic rams, and the counterweight system, I'm not sure if we're referencing a similar operational system to what we've got up at Hull, because we didn't want the counterweight system operating above the watercourse because of the impacts on the navigation. So that kind of discounted that option there. So which is why we ended up with the two rams as we've got at Ipswich, but as an updated version with a horizontal orientation. Don't know if that answers the question sufficiently. I'm sure you can come back and let me know.
Yeah, well, can I come in just briefly there?
Sure.
I think you've got to remember, we highlighted it in our presentation, that a massive advantage of hydraulics is power to weight ratio. And, these days, if you're going to build a significant structure such as this, my thoughts are, and we weren't involved in this, but my thoughts are that you would typically consider hydraulics and the direct drive from hydraulics because of the expense, the difficulties, the ongoing maintenance of counterweight systems. So for me, because of the power to weight ratio advantages, it would be a no-brainer, and you would go for hydraulics. Even though it's a much bigger cylinder, you would still go for them. So that would be my answer to that. Thank you.
Okay, thanks, Paul. Adam, in terms of the design life of the barrier, can you just, someone's just asking what that was, what the original design life will be?
So the design life of the barrier itself, so we've got a 100-year design life on the forecast levels of sea level rise, so that gives us our 7.55. The barrier itself has some key intervention points and operational maintenance packages at 25, 50, 75 and 100 years. So the barrier itself should last for the duration, so we've taken into account corrosion limitations on the steel, but also within the paint specification that we've got on the barrier, that takes that into account. We do have electronic electrodes as well on the barrier and the surrounding areas, just to give that additional levels of protection.
Okay, so for example, things like the removable U-shaped hydraulics which cross lines, something that would get replaced every sort of 25 years?
Sorry, yeah. So the big U, shall we say, so it's stainless steel. So the reason we've done it in a single piece is so that it can be lifted out. So that will be part of the inspection regime. So I'm not quite sure the design life itself on what it's designed to, but through the inspection regime, if we are noticing areas of corrosion, then the plan would be that we'd manufacture a new big U off-site, we'd bring or adjacent to the barrier, and that would be lifted in a single river closure. So the way that it's been designed and installed is we've got flexible connections only at the top, and the recesses that it sits within the concrete superstructure. The protection panels will be lifted off. The big U would be disconnected from within the structure. That would be lifted out in one go, and new big U would be put back in and then reconnected with the flexible hoses at the top. So it's all been designed for ease of exchange and renewal in the long term over that 100 years.
And with the removable plates above the big U,
okay, thank you.
Regularly, can't it? Without the need to remove it.
Yes.
Okay, we'll just ask a couple of final questions. Someone's asked what's the maximum height the sea level can rise that the barrier can still deal with. So I'm assuming that means, based on its kind of existing design height for the existing water levels, how much kind of capacity have you got on hand?
So the current sorry, I'm just reading it. So the design level is 7.55 meters. So we've got a small amount of freeboard on top of that. So we're running at about 7.4 meters for the forecast 1 in 300 year level. So the next 100 years. The current levels that we operate from, so we'll be operating the barrier from 5.3 meters. So we've got sort of 2.2 meters of sea level rise in there.
Okay, thank you. And the final question's on how effective is the seal that sits between the barrier and the bank of the river? How much are some of the sides or at the base on the riverbed?
So there is leakage around the barrier. It's not a fully sealed barrier. I can confirm the leakage rate, not today because it's not a figure that I recall off the top of my head. But we do have a leakage requirement. What we have upstream of the barrier is a fixed system up to Grand Sluice. So that area, if the leakage basin, so we say, is more than capable of accommodating the leakage rate through the barrier. And as we only envisage the barrier closing for the duration of the tidal surge, as soon as we get the surge receding, we'd be opening the barrier as soon as we possibly can when we get parity in water levels upstream and downstream. So we don't see there being any issues with leakage around the barrier and then potentially impacting on Boston.
Excellent, thanks, Adam. Okay, I think we'll bring tonight's talk to a close. I'd like to thank Paul, Adam, and Ian for the time and the presentation tonight. Really interesting. Thank you to everyone who joined us to ask questions. That's it, really. Say good night to everyone. Hope we see you again at one of our future events. Thanks very much. Good night.